subject of retirements, we are incredibly delighted to have enticed out of retirement our first speaker, who is Professor Phil Dawid, Emeritus Professor of Statistics here in Cambridge. And I don't think there's anybody who has worked in Bayesian nets who has not been greatly influenced by Phil's work. And in particular, Phil is one of the people who pioneered the work of Bayesian nets in forensic science. So I'm delighted to welcome Phil to introduce the program for us today.
Thank you very much, Norman. Is that working? Good. So this is, as it says, an introductory lecture. You're all here for a workshop on Bayesian networks. Some of you will be saying, what on earth is that? So some of you will be completely familiar with it, in which case I'm surprised you're here in the first place, but you please don't snore is my only request. But it's going to be a mixture of the basics of Bayesian networks and some idea of their specific applications within forensic science. So what is a Bayesian network? It's something which comes with various different names. I actually quite loathe the term Bayesian network because there's nothing especially Bayesian about a Bayesian network. I had a conversation once in the Watergate, which some of you may have heard of, with Yuda Pearl, who was responsible for introducing the terminology, and tried very hard to persuade him that it wasn't appropriate. And he said, oh, well, I was doing Bayesian things when I introduced the terminology. So, but we're stuck with it. A Bayesian network or a BayesNet, used interchangeably, BN in both cases. When we started working on this many years ago, we used the phrase probabilistic expert system, but I think that's a bit old hat by now. But one thing which is important is the actual mathematical structure which we're dealing with, which is something called a directed acyclic graph. More precisely, an acyclic directed graph, but that's a bit harder to pronounce as an acronym. So, we have the idea, it's a way of describing and talking about and explaining and manipulating and computing with complicated probability distributions which have complicated dependence. But to simplify that so that you can actually deal with it. So basically what we're talking about is a way of representing, describing, computing with a large multivariate probability distribution, which is, if I just say that, it's one big mess, but we have to try and get in there and clarify things and get inside and get rid of the mess. Very specifically, we do that by making use of conditional independence properties between the variables that we're talking about. That is a unifying factor that allows us to take a big, complicated picture and break it down into lots of smaller pieces, which we can then handle separately and then put back together. That's the principal idea. Divide and conquer. Take a big problem, break it into lots of little ones that you can understand, and finally put them back together again. This may be less relevant for forensic purposes, but there's a big enterprise out there which is trying to interpret such diagrams as representing causality in some sense. If I have time, which frankly I rather doubt, I will say something about that at the end. Okay, so a bit dubious about that. The other interesting thing about it is, if we think of specifying sort of in algebraic terms or numerical terms a big multivariate distribution, it's all quantitative. We write down probabilities, joint, conditional, whatever. It's a big mess of numbers or symbols or whatever. But there's also a qualitative structure, the way things are relevant to other things, the way things are related or unrelated, which has nothing really to do with the numbers. And the nice thing about Bayesian networks is it really separates out those two aspects. And you can focus on the high-level qualitative aspects of the problem before getting bogged down in the numbers. In fact, there may be, for some purposes, where you don't even need to think about the numbers in the first place. Okay. So, there's a story which is also up on the screen here. Some of you will be able to see that. And I'm going to use that as an example. So this is a made-up story of a crime, but it's reasonably typical, I think. So, to go through it, an unknown number of offenders entered commercial premises late at night through a hole which they cut in a metal grill. Inside they were confronted by a security guard who was able to set off an alarm before one of the intruders punched him in the face, causing his nose to bleed. The security guard said there were 4 men, but the light was too poor for him to describe them, and he was confused because of the blow he had received, so maybe it wasn't even 4. And then about 10 minutes later, the police found the guy who was currently up in court, the suspect, trying to hotwire a car in an alley about a quarter of a mile from the incident. He denied having anything to do with it. That's all eyewitness evidence in the case. There's other evidence, fiber evidence. So a tuft of red acrylic fibers was found on the jagged end of one of the cut edges of the grill. And the suspect's jumper was also red acrylic, and by various different tests, it wasn't possible to distinguish the fibers on the jumper from the fibers on the grill. And then there was blood evidence. Might be DNA evidence, but it's also to do with the pattern of blood. There was a spray pattern found on the suspect's jumper, and when the blood was typed, it was different from that of the suspect, who was wearing the jumper, but the same as that of the security guard. Okay, so what do we make of all that? Well, what we're going to try and do is express the relationships between all these variables in a form. So I think I've got that there, so you can see it twice. So this is a graphical relationship, and I'm not going to go through everything, but for example, so in a certain intuitive sense, the arrows represent dependence. So each node represents a variable of interest in the problem. The square ones are the ones I've talked about. They represent things which are evidence in the case. So they're all there. And there are a few others knocking around, which are other things to make sense of the story, although not necessarily observed. They're not observed. So one thing of interest, but we haven't observed, is who left the fibers on the grill? In particular, was it this suspect or one of the other suspects? Or was it somebody completely different? Who left the blood spray on the jumper? We don't know. Whose blood was it on the jumper? Sorry, this was whose blood was it on the jumper? And this was, what was the type of blood? Was it a spray or a squirt or whatever? This is the pattern of the blood. We're not even quite sure how many offenders there were. The guard said 4, that's his evidence, but he was a bit confused at the time, so that's an unknown quantity. And rather important is this node, is the suspect guilty? Was he one of the offenders? That's what we really care about. And the whole point of this is to get some evidence about whether he was guilty or not. So this is a purely qualitative representation, a way in which different things depend on other things. And we'll come back to this and describe it in various different ways. But you see there's the evidence, the eyewitness evidence over here, all on top, fiber evidence down here. So this is the measurements on the fibers from the jumper, the measurements on the fibers discovered on the grill, and that will depend. So what was discovered on the grill will depend on 2 things. If it was this guy's jumper, then basically the grill fibers would almost certainly match the jumper fibers, and if it was somebody else, then there'll be a different relationship. So that's the kind of thing we're talking about. Okay. So the basic structure, as you see it, is we have a set V of nodes. All of these things are the nodes, and each represents a variable of interest in the problem. And there's an art form. There's, thinking what are the variables which are relevant to your problem takes a bit of time and effort and thought. And obviously there are things that you observe, there are things that you care about, like is he guilty or not guilty, but you might have to throw in some other variables too to tell a sensible story. And then we have these arrows, so these represent in some intuitive sense influence or dependence, so these arrows, so the arrows from A. So we also use a sort of mock genetic terminology. Whoops, that won't do. So we can call A is a child node with parents N and C, because arrows come into A from N and C. Right, and it's an acyclic graph. That means there's no way of following the arrows round and getting back to where you started, because that would be a bit well, there are other graphical representations which do allow that, but this is much easier to interpret without that. And that's all the qualitative structure. And if we want to get quantitative, we've got to put some numbers in, and what we would do is for each node we would specify how it depends on its parents by means of a table of conditional probabilities. So we'll say whose fibers are on the grill, how does that depend? Well, if the suspect is guilty and there were 5 suspects, who knows? Well, of course, it could have been one of the other guys. So maybe we'll say it's one chance in 5 that it was his fibers. There will be various things. Some of these numbers are you've got to think hard about. Some are really quite hard, and you can argue quite seriously that they're in the right ballpark at any rate. Others could be much more tentative, and you can have discussions about what are appropriate numbers and do sensitivity analysis. But we'll put in such conditional probabilities. And intuitively, as I say, we think of the parents as influencing the child, whatever that means. And it's rather tricky to make that absolutely logically rigorous, actually. I'm not necessarily talking about causal influence. And if I'm not, then what am I talking about? Well, we have a sort of intuition about that, so I'll leave that fairly vague. But what is important is that the representation is not vague. It's very clear about what it's saying, and we have ways of manipulating this representation. So how would we actually construct such a graphical story? Well, we have to take the variables in a suitable order. That would generally be fairly obvious, though not necessarily sort of what comes logically before something else. So the guard's evidence of the number of offenders will presumably depend on the number of offenders and not the other way around, for example, and in effect, so there's an arrow in that direction. So we take them, we put the sort of founder nodes, which are sort of the basic things, and other things which hang off them. So we take them in a particular order, and as we introduce each new one, like A, we think what are the variables which will influence that? The ones we've already introduced which will influence that, and we draw the arrows. And the ones which aren't connected by arrows are not relevant. Once we know the so-called parents in the graph, anything else which we've already introduced is supposed to have no influence. You don't need to know it. It makes no difference. So go back to B. Whose blood was it on the jumper? Will depend on... so we've introduced these top ones already, but we could have introduced some others. We certainly don't want to have introduced something which hangs off it. What type was the jumper, the blood on the jumper? But as far as it depends on other things, it only depends on whether the suspect is guilty. Was he there at all in the first place? If he wasn't, probably it couldn't be his blood on the jumper. And if he was there, is it his blood or one of the other guys who did the punching? And so, and it wouldn't depend on what the guard said. It would depend on the actual number of offenders, and it wouldn't depend on what the police said about this guy hot wiring the car. Just not relevant. Okay. Anyway, having specified those, we draw the arrows from parents to children. And one child can have 1, 2, 25 parents, which is biologically implausible. And when we finish that, we end up with a picture like this, which is, it has to be a directed acyclic graph, where you can't go around, because we've taken them in a particular order, introducing one at a time, we can't get back where we started. And at that stage, should we wish to, we can introduce the numbers in terms of conditional probability tables. We look, as I've already mentioned, look at any node and think about how quantitatively does it depend on the states its parents are in, and do the conditional probabilities. But the whole point about that is we're doing it at a very local level. So if I'm thinking about y1, although that is a variable with a joint multivariate distribution with all the other variables in the problem, that's too much to specify. All I need to specify is how it depends on its immediate parents in the conditional probability table. So local specification, I say breaking a big problem down into little itty bitty pieces, which we can specify, and it can be shown very quite trivially in a way that that specification, together with the assumption about the way in which things are relevant or irrelevant to other things, completely fully specifies the overall distribution of everything. So that's the way to get the big problem out of the little one. That's determined. Right, I'm going to talk a bit more about the purely qualitative aspects of that, because that's quite important. So we have that picture, and with the way we've constructed it, is any variable like A is independent. Well, I don't want to introduce evidence that comes from below, because that messes things up no end. But if I just look at so-called non-descendants, so I'd exclude y1 from A, but everything else is allowed, then it says it only depends on, so A only depends on its parent, so conditionally on everything, it's independent of all the rest given N and C. So those are things we sort of built in by construction of the graph. But it turns out there are other things which are implied, which can be read off, which are mathematical consequences, which we might not be aware of, and it's quite interesting to discover. And there's a routine, a very straightforward routine for finding them. So this is the notation for conditional independence. This says that the set of nodes A, one or many, is conditionally independent of the set of nodes B when I condition on, tell you about, values of the nodes in C. So we can look at the graph and we can discover what's that true. So I'll run through this in this particular case. So first of all, we've got these A, B, and C we care about, and we ignore everything except these nodes and their ancestors, their parents, grandparents, and all the rest. Everything hanging down, don't care. Now here's the I don't know. Stefan Lauritsen and David Spiegel, I think, regret having coined this terminology, but it's called moralization. If we find that a child has two parents which are unmarried, in the sense that they don't have an arrow in either direction between them, we draw a line between them, we marry them. And it's not very moral if there are three of them involved, of course. And then, having done that, we just ignore the arrows which are left on the other, and we're left with an undirected graph. And finally, we see, in that undirected graph, can we find the path which goes from somewhere in A to somewhere in B and avoids C? And if we can, we haven't proved anything, but if there is no such path, we can indeed deduce this conditional independence. So the best way to explain that is by example. So here is a schematic of exactly that picture. I hope, yes. And what I want to do is query this particular conditional independence. In the multivariate distribution represented by that picture, can I deduce this conditional independence? So here's what I do. First of all, well, let's look at, there's B and R, where are they? B and R are here. G1 and Y1 are here and here. And A and N are here and here. What I'm going to do, ignore everything which isn't one of these or one of its ancestors. And that gives me a slightly smaller graph called the ancestral subgraph. Still the same query. Now I look for immorality in the problem. Oh boy, A and X3 are both parents of Y1, and they're not married. We can't have that. So we're going to marry A and X3. Likewise, we're going to marry B and G2. Everything else is okay.
No, G1 and C.
Sorry, it's not G1 and
C.
No, they're not parents of the same thing.
Around.
They may be. It's not immoral to be children of the same parent.
Or of your mother and grandfather.
Yeah. Anyway, let's continue. So we do that. So as you can see what I've done, I've put in those moralization, those marriage links, and I've just ignored the arrows. So those are the stages. You take the ancestral subgraph, you moralize it, you ignore the arrows, and now we say, can I go from any node in here to any node in here, avoiding A and N? And you'll see you can't. Can I get from either B or R to either G1 and Y1 over here? Any path from B and R to one of those has to go through N or C. There's no way it can avoid. In fact, any path which goes from here to there has to go through either N or C. Whoop, 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 whoop. And so what we've done is we've proved that that is actually true. Yeah. So there's no such path. So you can query the graph. This is the lovely thing to do. It's purely qualitative, don't need any numbers. What it does is it looks for implied conditional independence properties, which are applied by what you fed in but might not be obvious to you in the first place. And we can use those in all sorts of useful ways. For example, here's a nice example, to still simplify algebraic computation. In exactly the same way that I've described to you, but I won't go through in the same boring detail, we can prove all these different conditional independence between various subsets in the problem. And I can use those to simplify things. So, for example, this expression is a sort of ingredient of a likelihood ratio. You need a bit extra, but in fact, to make this really work, we've got to add an additional non-graphical assumption that the guard wasn't so confused that he couldn't count. So let's just assume for simplicity that his evidence of how many offenders there were is accurate. Otherwise, it gets much more complicated. But it's reasonable. And then I've left N out of it. N and G1 are now the same. So what happens is this complicated expression breaks down into itty-bitty pieces like that. And that's, I've used the various conditional independences in two different ways, actually. One is to I hope this is right. Yeah, I think it is. It's a ratio, so various things are going to cancel. The main thing is that it's comparing C, that the guy's guilty, and C bar, that he's not guilty. So it's a kind of likelihood ratio. And lots of things are going to cancel. And also conditional independence. Well, independence gives me product forms, and it also gives me simplification of conditional probabilities that various terms don't have to be there. And so various terms in the condition. So that's a nice simplification. And we can use that. And in fact, there are other things we can add to which aren't represented in the graph to simplify even further, but that's a good start. Okay. Now, here's an important point. The idea of such a graph is it represents a big multivariate distribution, and in particular, at a qualitative level, it tells you what are the conditional independence properties that are built into that distribution. And it turns out that it needn't be unique. If I say that's what I want to do, build a directed acyclic graph which is interpreted in this way as giving you conditional independences, is it unique? No, it isn't. And I'll give you some examples. So you take two different graphs are called Markov equivalent if they actually represent the same structure, the same conditional independences. And it turns out that they are Markov equivalent if there's an easy condition to see if it's true. First of all, if you just ignore the arrows and look from far enough away with squinting your eyes, they look identical. Same skeleton, as we call it. And secondly, we've talked about these immoralities. Immorality is a configuration in the graph where a child has two unmarried parents. If you see that configuration in one graph, the identical configuration with the arrows in exactly the same has to be in the other. Other arrows might be in different directions. So here's a very simple example involving three variables. One, A goes to B goes to C, the other C goes to B goes to A, or B goes in both directions to A and C, or A and C go in to B. And you see, they all have the same skeleton, which is just a line from A to B to C, where we ignore the direction of the arrows. But they don't all have the same immoralities. There are no immoralities in 1, 2, or 3. There is no instance of two parents having a common child. So they satisfy the criteria. 1, 2, and 3 have the same skeleton and the same immoralities, namely none, and therefore they represent the same property. Whereas 4 does have an immorality. A and C are the unmarried parents of B. So that's different. And indeed, 1, 2, and 3 all represent that conditional independence, that A and C are independent given B, and by putting any distribution with that property, if you make the numbers work out, could be represented by any one of those 3 equally. But 4 is different, and it represents a distinct conditional independence that unconditionally A and C are independent and B doesn't enter the story. So what that means is it's a bit tricky to interpret what these arrows mean. The arrows, I like to think of them as an architect's construction lines. If you get an architect to design you a house and he draws you a diagonal across the room or something to make sure there's a right angle, you don't want to see that diagonal in your sitting room. Okay, it's just part of the story. It's part of the representation, but don't interpret it as being out there in the world. It isn't. All these arrows do is they allow you to apply this routine of forming the ancestral set, doing the moralization, and checking for conditional independences. They don't mean anything other than that. They're just construction lines. The direction isn't important as long as it does the job. So that's why I'm rather, although I said when you construct this you think about influence, but we're not quite sure what that is. But if we try and understand the arrows as representing in some deep sense influence or causality, I think we can be misleading ourselves. They actually represent conditional independence. And one nice thing about conditional independence is a completely symmetrical relationship. If A is independent of B given C, then B is independent of A given C. Which isn't shown very well on that picture, which looks, because having an arrow pointing from A to B is a very unsymmetric relationship. But it's a fiction, it's just a construction line. It's just your diagonal. Okay. Right, I've talked a lot about the qualitative structure, and I've also mentioned that the quantitative structure is thereby determined. What time do I have to stop, by the way?
Till 11, but if you want some questions.
Yeah, okay, all right, okay. So I'm not going to give the detail, but there are efficient and I think very elegant computational algorithms for taking the bits you specified of the little itty bitty pieces, these little small conditional probability tables of a child given its parents, and putting it all together inside a computer system that you don't want to peer too closely into, and pressing a few buttons, and you ask, what is the margin? If I put in this information on these variables, the evidence nodes, if I tell you all these red variables where I throw in the data I got here and say, what do I now believe about the probability the suspect is guilty? That sort of thing. You get that out. We have lovely technologies for doing it. Marginal distribution, or what I've just mentioned, conditional distribution given some values for other variables, which is we can call evidence propagation. Put in evidence, so what's its influence on other variables which are still unknown? That's the important aspect we can do. And there's that's the commercial break. Okay. And there's lots of software out there, some of it proprietary and expensive, some of it freely available to play with, to do that. Now, in the last 5 or 10 minutes, I'll say about a particular form of Bayesian network, which is very helpful, really as much for the user interface. It doesn't really sort of change much about what's going on at the deepest level. Everything I've said already is relevant, and the computational algorithms are essentially the same. But the way you describe and interact with the system is made much more user helpful, shall we say. So here's an example. Paternity testing. I suspect things like this will be coming up again this week. So here's a query. I have DNA from a certain child and his mother. And the mother says, oh, this is his dad. She points the finger at this putative father. But there's doubt. There's a case, but there's doubt about that. He said, no, it wasn't me. And she, what about all the construction workers? So, some of you will know that story. So, well, one thing we know is the child certainly had a father, a true father. But we're not quite sure who he was. So here's the true father and here's the putative father. They may or may not be the same person. So that's the query. Are they the same or not? So a rather trivial little pedigree describing disputed paternity. Now, when we first worked on this, we sort of represented it this way: that this is the putative father's paternal gene. So each individual has two genes. You're looking at a particular marker, one at a time. Well, forget, you'll actually, of course, combine them in the end. But a particular genetic marker we'll call a gene. And we measure, the putative father has two, a paternal and a maternal gene. Although we know we can't tell which is which, we actually observe the genotype, which is putting them together but not being able to tell where they came from. So that's a sort of simple logical connection, but with a bit of forgetting about the order going on. Likewise, there's her paternal and maternal gene. And the genotype, which we can observe the genotype, but we can't observe the individual genes. There's the child's maternal gene. Well, it's drawn at random by Mendel's law, essentially by tossing a penny and choosing one of these at random. So you can sort of build up these things. So at each one of these gene nodes, the sort of founder nodes, we would put in there's a quantitative structure, which is basically the probabilities of the possible values, possible states. And all the other nodes are simple logical relationships or coin tossing or whatever, or we combine these together. So here's where the data is, and this is what we care about, the query node. So we can do all that, and we do, and it's quite simple and straightforward, and it works out nicely. But there's some numbers for one of the for gene frequencies. But we can actually do it in a slightly more appealing way using the so-called object-oriented Bayes net. So what we have, a generic node for a founder, somebody in the network who hasn't got any parents represented in the network. So the putative father, an alternative father, if it wasn't him, and the mother are all founders. There's something for a child where the parents are represented, and there's a generic network for that. And there's a query node, which is basically saying, was it this one or that one? And there's this one, which is, we care about the actual query. And so these are each of these is an instance of something we've built elsewhere, and it's repeated because it's the same structure. So the idea of the object-oriented network is something which is going to be repeated again and again, we only have to put in once and reuse it. I don't know how much detail I'm going to go into. The lowest level, we just have a gene with its frequency table. The genotype generic network is pretty trivial. We take the paternal and the maternal genes, and we forget their order by just looking at which is the larger, smaller, and which is the larger, and then we won't know where they've come from. The meiosis, this is Mendel. If it says the child's gene, if we know the paternal gene and the maternal gene, so we've got this is a coin flip. Is the child's gene going to be inherited from the father, yes or no? Okay, 50%. If yes, we just copy the paternal gene. If no, we copy the maternal gene. So this is the kind of thing we can build up, and they're very simple and quite natural. We can we can build a founder, his genotype, founder's genotype. I'll go quickly through these. A child, the query, and then we can put it all together. And now, not only in the same network can I repeat these things which come over and over again, I can reuse them like a child's construction toy to build more complicated stories. So here is a more complicated story where I have there's the disputed child. There's sorry, this is not much data here. There's a child. I thought we had them. Okay. There's this. There's the. We don't get even to see the putative father. He's gone away. But we get his brother. So there's a grandfather or grandmother. Anyway, it's a complicated story about we get distant relationships, and we got to see what can we say. But the point is, we can build this. We've already constructed these founder nodes, these child nodes, query. All we got to do is point and click and put them together, and we can tell lots of different stories. So that's kind of neat, and we can analyze that. So in fact, in the particular case, we do this once for each of 12 markers, and we end up multiplying likelihood ratios because we regard them as independent. We go to our favorite computer system, put in our evidence of what we've seen, the genotypes, propagate it through the system, and hey presto, we can get a likelihood ratio. And for the data that was done on the case which led to this, likelihood ratio in favor of paternity of 1300. Another nice thing about these object-oriented Bayesian networks is you can elaborate them. So instead of saying that the child's gene is always paternal or a maternal gene, we allow for mutation. Maybe something changes on the transmission, and you can throw in procedures inside there, which you just go into that little bit that's relevant and fiddle around with that. Or you can have silent alleles, which means something which for some reason was there but didn't get observed by the technology. There's a whole thing about mixtures, which I'm sure we're going to hear a lot more about in the rest of this week, and so on and so on. And one other, just to finish, the thing which really got me into this area in the first place, many, many years ago, I went to a lecture by David Spiegelhalter, Sir David Spiegelhalter, who I don't know if he will show himself, he's just across the grass here. And he was, I think, thinking about developing the bug system at the time, some of you will know. And he did this thing where he said, well, we don't have to distinguish between observable variables and unknown parameters. If we're Bayesian anyway, everything's uncertain. Why don't we put them all in the same picture? That was a revelation to me. Wow, yes, why don't we? Never thought of it. And you can. I mean, so I haven't done here, but you can actually say that these variables, x, u, and x and u, they're sort of, they could both be. This is a founder, this is a child. There's something to do with allele frequencies or mutation rates, possibly. And the same variable goes into each. This is in Bugs notation, this is a plate which is repeated over and over again. It's just like an object in our object-oriented system which can be repeated over and over again. And we have the same thing. And in principle, sometimes the computations grind to a halt, it's true. But in principle, you can do that. So you can do completely Bayesian things. And if you can't do it with the exact computational routines, then you can go to bugs and do some Monte Carlo simulation or whatever. There are all sorts of ways you can get at that. Now, as I predicted, I haven't got time to talk about causal diagrams, but I would just say this. As I said, there's a strong temptation to interpret those arrows as causal. Beware! If you want, there's a lot to be careful about. Okay. I'm going to skip because time is up. If anybody wants to talk about it later, we can do that. So, a few cautions about the use of Bayesian networks. First of all, it might not work at all. The problem just doesn't lend itself to this kind of representation. As I'm pointing out, what look like different structures can represent the identical distribution, but we know how that works. If we took the variables in a different order and did the construction, we might end up with different things, some of which encapsulate some of the conditional independence in the problem, ignore others, and vice versa. We've got these lovely computational algorithms. The exact algorithms can grind to a halt, even in very fast computers, depending on just how small the itty-bitty pieces have got to be. And as I say, beware the temptation to give a causal interpretation to the arrows. Thank you very much.
Time for a couple of questions.
Thank you for an interesting presentation. You mentioned as one of the cautions that not all problems are for Bayesian networks. Can you give a hint at which kinds of problems are and which kinds of problems are not?
Well, I mean, there's some problems where there's no obvious dependence or independence properties at all. It's just a great big mess. And if you build the Bayesian network, everything, arrows will be pointing from everything to everything else, basically. Or you can have, in image processing, you might represent your pictures on your computer screen by the relationships between the pixels, two-dimensional arrays. You say the color I'm going to see at this particular point depends on what's around it and nothing else. That's quite a nice, simple conditional independence property, but those things cannot be represented by Bayesian networks. So it's quite special. There are other graphical representations which will deal with some of the other problems, but they're all limited in one way or another.
Suppose there's some temporal ordering in the underlying events you're trying to model. Will the arrow always go from the prior event to the subsequent event? Can it ever go the other way?
What you're doing is building a mental model. You're not describing the world, you're describing your picture of the world. Now, my pictures of the world generally have influence going from past to future. I don't know about yours. That's all I can say.
So, when you do the object-oriented Bayesian networks, then you get a very nice deck. You take a very complicated model and you wrap up some of the pieces, and now you have, like the construction set you made, you get a very simple graph. How should I check all the conditional independencies there? How should I think of the nodes?
Oh,
you're hiding away.
Yes, you've hidden a lot away, I mean, which is a good thing, but there are some purposes for which you need to delve deep down. And you can flatten it. I mean, you can actually say, what you've done is an object-oriented representation of what is still underneath it all, one great big multivariate distribution. And you can look at that. It's probably almost impossible to interpret, but you can look at it, you could do your moralization stuff on that if you need to. It's a good question, actually, about whether whether we can use the high-level structure to simplify that. I haven't thought about that.
So in your construction set picture, it was quite simple because I think every network would only, so it was like the maternal genotype or whatever, like that would only have one link to the other nodes. So probably the independent structure there can actually be read.
Yeah, I mean, you could say that the nodes inside one of those things, you could treat them as a block. So if I just say everything inside here, I mean, I could, as one big collection of variables, I can go at that level, I could get conditional independence using the standard methods.
Yes.
But if I want to look individually at things related to some of the things in there and some of the things in there, well you might need to go deeper down.
And if you want to check your assumptions, like if you present that to me and I want to assess whether your assumptions in this case were true,
Yeah.
I would kind of have to unfold it and look at everything right now.
I mean, a lot of it, I think, can be done at the high level. You say, that this says that given all there is to describe about the grandfather's genetic type and the grandmother's, whoops, it's gone again, that the genetic type of the putative father and his full brother are conditionally independent because they both inherited from the same parents, but independently. We believe that, I think. So, yeah, we can do a lot at this level.
You said these Bayesian network models represent our mental model for our view of the world. Aren't those models causal most of the time?
That's a good question. I mean, I think we do tend to have causal intuitions and think about dependence, and I've tried to avoid saying what that means because philosophically I think it's quite problematic. But yeah, I mean, we are thinking causally a lot of the time. But that doesn't mean to say that it's wise to put too much causal interpretation on these models. Yeah, I think at the construction level there has to be that. But and sometimes I think I'd rather not go there actually, because I suspect these kind of causal models are very interesting for lots of people, are of limited interest in forensic analysis.
Okay, thanks. Your Bayesian net representation there is a very nice example. But since we're being Bayesian, one can also wonder what is the prior probability
Ah, yeah.
that that is an appropriate model.
Oh, prior probability is an appropriate model. So,
And I'm thinking of one particular aspect of it, which is the jumper blood type. In that network, if the jumper blood type turns out to match the victim's blood type, that becomes very strong evidence of the guilt of the suspect.
well, it's evidence, yes.
But one can ask, are there other ways in which he could have got that blood on his jumper? And one of the questions about that would be, how old is the blood stain on the jumper relative to the date of the event?
Okay, if that evidence is available, it could be relevant, and it could be added to this network, or the network can be modified accordingly.
Supposing the evidence is not available, but it's a possible explanation. For instance, a suspect would say, well, my girlfriend was in the pub and a man there broke glass and cut his hand and
Yeah.
got on my girlfriend.
Okay, well, that would be additional evidence, because I mean, you know, somebody said something. That's evidence. That should be in the picture.
Yeah, but that's if he says it, but
If he doesn't say it, then it may not be relevant. If you don't know it, then I'm not quite sure how you're going to use it. I mean, but there are things here which aren't evidence, which are just helpful to tell the story, and it might be helpful to put that in to structure everything else.
if it is a potential different explanation which you happen to have thought of without evidence, then perhaps it should go in.
By all means, I look forward to seeing your alternative construction of the story.
Mine was a very similar thing, really, because in a real forensic scenario, your nodes are really very complex. I mean, the grill fibres and the jumper fibres and the blood type and the blood stain are enormous problems, and they are multivariate in themselves.
Yeah, good point.
Are you assuming for that model that you have identified the fibres correctly, you have identified the blood type correctly, and the blood spray is recognisable? Because as soon as you go into court, those are the things that enormous doubt will be put upon.
That's a very good point. I'm not assuming anything. Each one of these nodes could be an object in an object-oriented network with a lot of internal structure which introduces all those complications you talk about. I mean, this is a mock story. It's not a real story, but you're absolutely right that in any particular case there is more detail, and I think the object-oriented presentation makes it possible to put that in without getting overwhelmed by it and to take proper account of it.
But it's not real.
What do you
I
mean?
mean, that would be an unacceptable model for any court case.
Oh, I'm not suggesting you present this in court. Did I ever say that? I mean, there's a question about who is this for? Who's doing it and who is it for? I think it's probably for the perhaps to guide the police in their investigation, perhaps to guide the lawyer in preparing his case.
No, not for the lawyer.
Why not? It could be very helpful. Very helpful.
It's a far greater depth than that. That's
Yeah, okay, but it allows you. It doesn't stop you going into that greater depth. You can delve down into those nodes and put it in. But I think it's a top-down approach. I think is very helpful. You start at the broad structure, and then you say, well, now what further intricate detail do I have to think about? Drill down. Do that. Yes, please. Important. Good point. Thank you.
Christian, last one.
Okay, thanks. I'd like to return to the question of what the arrows mean. I know you said you didn't want to go there, but I mean, this is one thing that's always been personally unsatisfactory to me, that it's unclear exactly what the arrows mean. Because my worry is that if we're not really clear about that, then we might be asking the wrong questions when we fill in the tables.
Yeah.
So therefore, you said at one point that the direction is not important, but isn't it so? I mean, to take an example, suppose you would have, the hypothesis the husband killed the wife, and the hypothesis that the husband was jealous because she was cheating, right? So depending on which way you would put the arrow, you would either ask, okay,
He was jealous because he killed her?
No, he was jealous because she was cheating. Okay.
No, but if you put the arrow from...
No, but that's a hypothesis about a motive, right? He had a motive because he was jealous.
So alternative hypothesis then.
Alternative to what? No, one hypothesis is, a woman has been killed, and one hypothesis is husband did it.
Okay.
So, and then there is an hypothesis that he had a motive because he was jealous of her. We don't know if that's true. There might be some evidence for it, but these are two hypotheses, right? So, depending on which way I put the arrow, I would either be asking the question, okay, given that a husband killed his wife, what's the probability or likelihood that he had a motive of this kind? Or, given that a husband has a motive of this kind, what's the probability that he will kill his wife? So and it seems to me that if you're not really precise about the arrows, you might be asking the wrong question.
I think, you raise a very good point, and I think it's really two different questions. One is, in the actual formal representation, what is it saying? And there are ways of saying it doesn't matter whether I do the arrows in one way or the other way, as long as I adjust the probabilities, I can make them tell the same story. But that's unsatisfying from the point of view of constructing the story. For me, I say, well, obviously, whether the motive is a possible influence on the murder, and not the other way around. But that's something I think maybe, I'm hoping other people who will talk about argumentation, which of course is coming up for the rest of the week, will be able to say something about this. I think you might say it's one of the weaknesses in the whole story, that we have these sort of intuitions and they make some kind of sense, but to make them formal, I think is not easy, and I won't pretend that I've done it. But I think it's a very good point. Thank you.
Thank you very much, Bill. Excellent.